Good evening, class.
Hello, teacher.
Right? How are you? Can you clearly hear me and see the share screen?
Yes, teacher.
Right. Thank you. Shuming, all right? Right. Let's start class. Class, we are now on week 8. So far, so good. So far, not so good. All right. Class. Wait a minute. Something wrong. Okay. All right, class. In the last 2 weeks, we discussed the estimation part on multiple regressions analysis. To learn why do we need multiple linear regressions? Mainly because we want to select assumption number 4, zero conditional mean. We want to make Gaussian interpretations, right? To learn that, if you incorporate more independent variable into your model, it is more likely that zero conditional mean assumptions is met. However, when you incorporate more independent variable, there might be another issue. That is perfect collinearity. So in multiple linear regressions, again, the new assumption that you learn is no perfect collinearity or no perfect correlation among independent variables. All right? No perfect correlations or perfect collinearity among independent variables. As I told you, normally the modern statistical package such as data will automatically drop one variable if there is an issue of perfect collinearity. I will show you an example when it comes to data applications. All right. So all as estimators will produce unbiased estimate, will produce unbiased coefficient only if assumption 1 to 4 are met, especially assumption number 3 and 4, no perfect correlations and zero conditional mean. Class, in addition to zero conditional mean, you also learn another 2 terms, which is inductionity. It's the same as zero conditional mean. It happens when your variable of interest is endogenous, or when your variable of interest is correlated with any other term. When your independent variable of interest is correlated with other factors that do not include in your model. And we also call it omitted variable bias. Why? Because you omit the relevant variable. That is why it is included in any other term. That is why we call it inductionity, or zero conditional mean assumption is violated. Class, Last week, you also learned that if you include a relevant variable, your estimate is still unbiased, but you will obtain large variance, right? So, if, for instance, you face two problems, if you want to include more and more independent variables in order to relax zero conditional mean assumption, another problem may emerge, that is multicollinearity. And what is multicollinearity? Multicollinearity is another problem. It is not the same as perfect collinearity. Perfect collinearity when two problems are perfectly correlated. Multicollinearity is they are not perfectly correlated, but highly correlated. Right? I will again show you the example and how we detect it. So from last week, if you review the lecture note or the textbook, we can detect multicollinearity by using variance inflation factor, VIF. If VIF is lower than 10, there is no issue of multicollinearity. But again, if you guys have to trade off between multicollinearity and omitted variable bias, try to address omitted variable bias. What you learned from last week's class is that if you have large sample size, multicollinearity could be solved. However, omitted variable bias could not be solved with large sample size. All right. So finally, we discussed that if assumption 1 to 5 are met, we obtain unbiased variance, we obtain unbiased standard error. All right. Remember the equation of variance of the estimate is equal the variance divided by SS what? Divided by SSQ, sum of square total, sorry, SST, multiply 1 minus R square. All right. Any question, class, from last week? Guy, it is important for you guys to review the lecture. So I only briefly recap. Hopefully, you guys still remember something. Any question from last week?
Yes, sir.
Yep.
May you explain the R square in the variance estimate again? What is it?
The R square in the variance is the R square, not the R square of the regression of all independent variable on dependent variable, but the R square in the variance is the R square of another regression where you run the regression of your independent variable as a function of other independent variable. For instance, if you have 3x, right, x1, x2, x3, and x1 is your independent variable of interest, and that R square is the regression, is the R square from regression when you regress x1 on x2 and x3. Are you following me? For instance, all right. So the R square in the variance here is the R square of the function of your x of interest. Let's say x1 is delta 0 plus delta 1 plus x2 plus delta 2 x3. All right. So the R square is the power of explanatory variable of other independent variable on your independent variable of interest. All right. It is not the R square of the independent variable on dependent variable. Do I answer your question, David? So again, our normal model is y is equal delta 0 plus x1 plus x2 plus x3 blah blah blah. But that R square in the variance, which is a proxy of multicollinearity, it is measured by this. So it assesses the correlations of other independent variable on your independent variable of interest.
So it means we run on every
another regression.
run a regression on every independent variable, right?
You can run a regression of your independent variable of interest on other independent variable. Right? For instance, you're only interested in one, you want to only estimate, you only focus on delta 1, but for variant of delta 1 here, you can run the answer, you can just simply regress x1 on x2 and x3. Is that clear?
Yes, teacher.
All right. But again, when it comes to data, you don't have to do it manually to detect the the multicollinearity. I will just quickly tell you how to do it in Stata. And normally in regressions, the standard error will produce it for you. If you want the variant of the estimate, it's simply just the square of standard error, right? Any other question, everyone, before we move on? Let me delete this. This is highlight.
Teacher, could you touch on omitted variable bias more?
Again, omitted variable bias is just the key term. It's just a different term, but the meaning is the same as inductionity. It's the same as zero conditional mean. All right. For instance, if you want to assess the effect of education on wage, and you know that ability affect both education and wage. So if you cannot include ability in your model, if ability is not one of the X, you omit it because of you do not have data or because of you do not know that it is a relevant variable. When you include ability from your equation model, we call it omitted variable bias. And you learn that if we omit the ability, the estimate of the wage, the estimate of education on wage is biased. Is that clear?
Thank you, teacher.
All right. So it's important. How do we know it? Again and again, only reading can tell you. All right. For example, if I want to estimate the effect of education on wage, I have to identify what are those relevant variables that may affect the estimate of education ability. But normally, class, we cannot include ability, right? So whatever independent variable you include in your weight equation, there is always an issue of omitted variable bias because you cannot include ability. Sometimes say IQ. Some experts say IQ. So even though you include IQ, it might not be the real variable of ability. All right. Any other questions? Thank David for asking me the question. Any other question before we move on? So far, last week or up to now, you only know how to, to estimate and interpret coefficients and standard error as well. All right. Today we are going to touch on another important points. All right. Make sure now at least you know how practically how you should what should you do to obtain unbiased coefficient. What should you do to obtain unbiased standard error? How to interpret them. All right. Again, questions? Okay. If you don't want to talk, drop your question in the chat box. All right.
Teacher, I have a question. So when we omit the unbiased variable, we might face some problems, right, teacher? Teacher, can you explain like the problem that we will be facing?
All right, again, guys, I suggest you guys to have a look on last week lecture note when we discussed the issue of omitted variable bias. Somewhere, where is it? Last week. Up here, up here, up here, up here. Right, here. Here. Can you see my share screen, right? So last week, we discussed that, for instance, in this equation, weight equation, again, everyone, we want to estimate the effect of education on wage. But we know that ability is an important component that affect education and wage. Normally, all right, if you estimate the effect of education on wage, you need to include ability. Because normally, people who have higher education have higher ability. And also, those who earn higher wage also have higher ability. All right, this is, let's say, this is a true model. But unfortunately, because of data, we cannot include ability. So we estimate this model with wage is only include education, not model. So in this case, all right, if we include ability, we will obtain delta 1. But when we exclude ability, we will obtain delta 1 plus delta 2 multiply the delta 1. So in other words, we obtain bias estimate. We don't know whether this delta 1 multiplies delta 1 here is minus or positive. If it is positive, we see that the estimate that we obtain will be larger than what we truly want. We only want to estimate this delta 1. But if we exclude ability, ability will be included in error term. And hence, delta 1 will become delta 1 plus delta 2 delta 1. So it means that the coefficient of our model that we omit the relevant variable is biased. So we violate zero conditional mean assumption. We have an issue of omitted variable bias. This education is endogenous. Following me, Chimay? That the same questions as Davin earlier, and now I come back to the slide again. All right. So if you exclude or omit relevant variable, when we say relevant variable, the variable that correlate with education and the variable that affect weight. For instance, ability here. Ability also correlate with education, also affect weight, right? For instance, if you ask someone that do not have any education, they still earn wages, but it depends on their ability. Also, people who have higher education also tend to have higher ability than the other. For instance, among yourself, someone is better than the other. Why? Because of ability, right? So education is also correlated with ability. It doesn't mean that every one of you who study at the same batch earn the same money, earn the same wage. Why? It also depends on your ability, right? So if you exclude ability or omitted ability from this model, the coefficient that you obtain from only education is biased. Why? It partially include here. We want to estimate delta 1, but in this coefficient, it also partially include delta 2, which is the effect of ability. Chimeng, you want to say something earlier?
No, it's okay now, teacher.
All right. So in short, if you omit variable, if you omit relevant variable, it means that the estimate, the coefficient of your variable of interest, when I say your variable of interest, the independent variable that you guys want to focus on is biased. Again, look at this equation. True model, we only want delta 1. But when we omit ability, now the coefficient is not only delta 1, but delta 1 plus delta 2 multiply this. All right. So the effect of education on weight now is not only education, but partly from ability. So the coefficient might be larger than true parameter. True parameter. right? All right. So now let's continue to the second part. All right, we're still discussing on multiple regression analysis, but this time on inference. When we say inference class, we want to say some things for population. Remember, when we analyze using sample, we want to say something representative to population. For instance, if you want to estimate the effect of weight on education, all right, you collect data from a group of people, but you want to say that this is representative to the whole population of Cambodia. So we want to make an inference. All right. So today's lecture is the first part of multiple regression analysis inference. It's only the first part. So for today, we want to make statistical inference. Again, when I say inference, it means that you want to say something to population as a whole. Right? For instance, you want to conduct the study on the effect of wage on education on wage, but your population is all students from DIS, but you cannot interview everyone. If you can interview everyone, you don't need to run regressions. The population is enough, right? You don't have to say something else. If you interview everyone, you don't need to run regressions. But normally you cannot analyze population, you analyze sample. If you analyze sample on the behalf of the population, you need to conclude and say something to the population. All right. So for statistical inference in the regression model, we will need to discuss on hypothesis testings about population parameter. We want to say something from our finding, how it connected or how it close to the population parameter. Remember what I said, population parameter, it is also coefficient, but for population. When I say estimate, there is a coefficient for sample. All right. So for today, we want to talk about hypothesis test about population parameter. We need to construct confidence, a construction of confidence interval. You will learn this later. All right. But again, before we move on, before we make any inference, you remember one of the assumptions is that all estimators are from random variable, from random data. The data that you see is from probability sampling, right? From the random sampling, right? And you also know that from assumption 4 and assumption 5, we say that we assume that the expected value of error term is 0, meaning that it is not correlated. The error term is not correlated with independent variable, and their variance is constant, homoscedasticity. But to make an inference, we need another assumption. We call it normality, and that assumption is basically for their distribution, the distribution of the error term. All right. In order to derive that distribution, we did additional assumption. Again, this assumption is about distribution of error. Assumption number 4, it's about the correlation of error term and independent variable of interest, that is zero conditional mean. Assumption number 5 is homoscedasticity, which we assume that the variance of the error term is not conditional on any independent variable. But for this assumption is we want to make sure that the variance of the error term is normally distributed. If you don't remember what do we mean by normal distribution, you have to refer back to our statistical review, right? Mainly statistic review 2. All right. Let me go a little bit further. So in this case, as you can see in this graph, we mainly assume that the error term has normal distribution. When I say normal distribution, we expect that the error term has this curve. Has this curve with any of the x, right? As you can see here in this graph, right? It normally distributed either with x1, x2, or x3. If it is not normally distributed, if it is not normally distributed, it's gonna look like school on the left or school on the right, something like this. All right, but normally distribution is this. The error term should be normally distributed. All right, so the assumption R6 is normality of error term. We assume that error term is normally distributed. So we say that it is written as if this is normally distributed. It means the mean of error term will be equal 0, and it is independent from any of the x. So if it is normally distributed, assumption number 4 and assumption number 5 is normally met. So the assumption is very short, that we require assumption number 4 and assumption number 5 together, and we make assumption number 6. All right. So here, if it is normally distributed, we have error term, mean of error term equals 0, and variance of error term is constant, which means it is independently of x1, x2, or x3. It is not correlated with any of the x. All right. So it is again assume that the unobserved factor, the other independent variable that is not included in your model, and normally distributed around the population regression function. It is around mid. All right. So the form and the variance of the distribution does not depend on any of explanatory variable. As you can see here, we want to make sure that the distribution is not conditional on any x, but it is different from.
Buồn nãy nè này cô. Bon, tao mà sửa lắm đấy.
Rich, can you mute yourself? All right. So the form and the variance of the distribution does not depend on any x. All right. The distribution is not conditional on any x. If it is true, we say that in this regression function y given x, we have normal distributions where the mean from this regression is this. All right. The mean, the expected value of y is this equation, right? And the variance is constant. It's constant. Right? Let's discuss a little bit about normality assumption. All right. So again, the assumption number 6 is normality on the distribution of error term. So the error term again, guys, the error term is again the sum of many different unobserved factors. It's the sum of many different unobserved independent variables. All the independent variables that you do not include in the model are all in error term. So again, the error term is the sum of many different unobserved independent variables. All right. These assumptions is an empirical question. Why we say it's an empirical question? It depends on the data. It depends on your own model. It doesn't mean that every study faces this normality assumption. It depends on data. All right. However, normally we believe that at least error term should be close to normal if you have large sample size. If you have large sample size, this assumption is not a main problem. Let me give you an example of the example that this assumption cannot be held. For instance, about wage. All right, about wage. If you survey the people, it might be the condition that the wage is not normally distributed. All right. If, for instance, normally you may ask, and then you get, and then in your sample you may get that many people have low, for instance, low wage, and then just only a number of people get high wage. All right. So the data is school on the left, something like this. All right. Or because wage in some country like our country, we have minimum wage. So because of minimum wage, we can see that the data will be skewed to the right. For instance, we start at least. All right. It should earn, say, $5 an hour. So we start with this $5 an hour. Right. And then the data here, and then when We go to the right, more and more people get higher income. But on the left here, people at least earn $5 an hour. And if you look at the data, it's not normally distributed. All right. So in some case, if the data is not normally distributed, we can achieve it through transformation. Through transformation such as of the dependent variable, such as instead of using weight, we're using log, natural logarithm. I believe that at one point in the other lecture, I told you one reason of using log is to transform your data to have normally distributions. All right, to have normal distribution. And how can you deal with that? Normally, if you read the paper of the relevant study to your paper for now, you may see that, oh, this paper using log. If they use log, one of the reason is that they want to have normal distribution. They want to make sure that the assumption number 6 is met. All right, one of the reason why they use natural logarithm of that variable. Okay, important for the purpose of statistical inference, the assumption normality can be replaced by like sample size. So as I told you earlier, even though, for instance, you use weight rather than natural logarithm of weight, if you have like sample size, that is okay. Like sample size does not only address the issue of multicollinearity, also the assumption number 6, which is normality of the error term. All right. That is why if you read any good economic paper, they always use like sample size. They always use like sample size. All right. They always use like sample size. So if they use like sample size, the problem that they may face is only omitted variable bias, only inductionity. Right? Because no problem with multicollinearity, no problem with normality assumptions. Okay, next. So again, if assumption number 1 to assumption number 5 are met, what is assumption 1 to 5? Remember, if you don't remember 1 to 2, at least you should remember 3 to 5. But assumption number 1 is that is the estimator of all estimator is from random variable, from random data. Assumption number 2 is linear in parameter. Assumption number 3 is no perfect collinearity. Assumption number 4 is zero conditional mean. Assumption number 5 is homoscedasticity. All right, take note on that. If assumption 1 to 5 are met, we call it Gauss-Mankel assumptions. All right, Gauss-Mankel assumption. In the future, when you see oh, Gauss-Mankel assumption, always believe that, oh, this is the assumption 1 to 5. If assumption 1 to 6, we call it classical linear modal assumptions. All right, 1 to 5 is Gauss-Mankel assumptions. 1 to 6 is classical linear modal assumptions. So if under assumption 1 to 6 is met, all right, we can write the expected of delta J is normally distributed. Then we have the estimator are normally distributed around true parameter. This is the population parameter, right? With the variant that we derived earlier, the variant that we discussed last week. Remember the equation of the variant? It equals this delta square divided by SST minus 1. Multiply 1 minus RG square. Right? That is variant of delta G from last week. Right? So again, if assumption 1 to 4 are met, or let's say if the classical linear modal assumptions are whole, we believe that the estimators are normally distributed around true population parameter with variant that we derived earlier, with variant that is unbiased, that is correct. Hence, how we standardize our distribution? So the standard die of estimator can be written in this equation. Delta J hat minus delta J divided by standard deviation or standard error of delta J. And what is the standard deviation or standard error? It's just the square root of this variance, right? It's just the square root of this variance, right? So we obtain the equation for the standard estimator. So if this is correct, we have the normal standard distribution with the mean of the population estimator equal 0 and variance equal 1. All right, but the most important thing is to remember this equation. All right, this equation. All right, so we obtain the standard die estimator. We want to standard die. All right, next. All right, so in order to go next, the important is to understand the next, how we test hypothesis. In order to test hypothesis about single population parameter, in order to test hypothesis about population parameter, we need this T distribution from the earlier theorem. All right. So for theorem 4.1, the T distribution of standard estimator and the assumption 1 to 6 is the sample estimator minus the population parameter divided by standard error of the estimate, and that have the T distributions of T minus K minus 1. All right, so we say if standardization is done using estimated standard deviation, that standard deviation is called standard error. The normal distribution is replaced by the T distribution. All right, so now the T distribution is close to standard normal distribution if only if n minus k minus 1 is large. What is n minus k minus 1, everyone? Remember, what is n minus k minus 1? What do we call it? Does anyone remember? What do we call n minus k minus 1? Does anyone remember? What is this? N minus k minus 1. It is? It is? It is? It is degree of freedom, right? It is degree of freedom. Hopefully you guys, talk to yourself or at least try to recall back. All right, so from now, when we want to make an inference, when we want to test hypothesis, we rely on this T distribution. We rely on this equation. All right, we rely on this equation. If you don't know what earlier is, don't worry. The key points coming now. All right, normally class, we want to make an inference, and to make an inference always we need to formulate hypothesis. So we start with null hypothesis. All right, the null hypothesis. The null hypothesis for general hypothesis, see below it here. H0 is the null hypothesis. Delta J equals 0. What do we mean by delta J equals 0? The population parameter is equal 0 after controlling for other independent variable. All right, so what we discussed so far, you know how to calculate coefficient, right? But that coefficient is the coefficient from the sample. So this hypothesis is mean that is there any chance that your delta or your population parameter equals 0? Right? So null hypothesis stating that delta J, your independent variable of interest, has no effect on dependent variable. What is your independent variable? What is your dependent variable? You name it. For instance, if my independent variable is weight and my dependent variable is sorry, my independent variable is weight, and my dependent variable is, what did I say? Sorry. If my independent variable is education and my dependent variable is wage, so the null hypothesis states that education has no effect on wage. Remember, class, even though you have earlier, you know that your estimate is bigger than 0, different from 0, but you cannot say that the population's parameter is different from 0. Is there any chance that, you know, the population parameter might equal 0? Your sample might not be equal 0, but population might be equal 0. So to test this, we need to use t-distribution. But remember, always null hypothesis will start with your population's parameter is equal 0. All right? There is a chance that your population parameter is equal, sorry, the null hypothesis stating that the population parameter is equal 0. How do we know that? We need to estimate our coefficient. Is there any chance that our estimate from the sample equals 0? We need to do this. We need to check this. All right. So next, in order to test the null hypothesis that population parameter equals 0, we need t statistic. We need t value. And here, as you can see from earlier, t is about delta j minus delta j hat minus delta j divided by standard error divided by the standard error of delta j. All right. But here, our null hypothesis stating that delta j equals 0. So if you replace this 0, you will get t of delta j hat equal delta j hat divided by standard error of delta j hat. All right. So the t statistic will be used to test about null hypothesis. The further estimate coefficient is, all right, based on this equation, the further the estimate coefficient is away from 0, it is less likely that it is null hypothesis hold true. So based on this equation, if we have larger t, the larger t, it means that we reject null hypothesis. So to obtain larger t, only if we obtain large delta j hat. Okay, and this denominator, this depends on the variability of estimate coefficients, standard deviation. All right. So again, t of delta j hat equal delta j hat divided by standard error. It because of this equation, right? Because our null hypothesis, we want to test whether this delta j is equal 0 or not. If we replace this equal 0, we will obtain this. All right. So again, the goal is to define a rejecting rule so that if it is true, to reject null hypothesis or to accept hypothesis. But to do that, we need to discuss further. All right. It depends on your null hypothesis and alternative hypothesis. What type of your alternative hypothesis? All right. So we start with the testing again one-sided alternative greater than 0. So remember, if you have null hypothesis, you always have alternative hypothesis. In here, we have alternative hypothesis that assume that it is bigger than 0. All right. So here we test null hypothesis stating that the population parameter equals 0. We can add an alternative hypothesis that believes that delta j is bigger than 0. We only have one direction, and we believe that it is bigger than 0. That delta j must be positive. So we call it testing again one-sided alternative which is greater than 0. All right. This case, we only reject null hypothesis only if the t value that we will construct from earlier equation is bigger than critical value. Only if t is higher than c, we reject null hypothesis. So we reject X0. We reject X0 if T equal bigger than 6. What is T? What is T? T is from this equation, all right? Delta J divided by standard error of delta J. How about critical value? We will discuss later. All right. So we reject null hypothesis in favor of alternative hypothesis if the estimate coefficients is too large. As I said, if you want to obtain large T value, we need to have to make sure that we have large estimated coefficient, larger than critical value. So we need to have T larger than critical value. To construct critical value class, constructing critical value, we need some rejecting or significant level. All right. For instance, you construct critical value so that if the null hypothesis is true, it is rejected in, for example, 5% of the case. Meaning that, all right, the null hypothesis only true if what? If only 5% of the case is correct, it is equal 0. If there is only 5% chance that true that population parameter equals 0. All right. So you need to ask yourself, what is the chance that you want to reject null hypothesis? All right. For instance, in this example, this is the point of T distribution with 28 degrees of freedom that exceed 5% of the case. All right. Again, in order to understand this, let's move to the next example. Remember, we need T value and critical value to test our hypothesis. All right. In this way equations, we test whether after controlling for education and tenure, higher work experience lead to higher hourly wage or not. All right. So in order to do that, we need to construct T and critical value. All right. So in this case, our null hypothesis is that experience has no effect on wage. Our null hypothesis, we believe that experience has positive effect on wage. We reject null hypothesis only if T is higher than 6. How to construct T? Remember, T is standard coefficient divided by standard error, right? Here you obtain, this is the coefficient, this is the standard error. So next, here, T we have coefficient divided by standard error, we get T is about 2.41. How about critical value? The critical value is the point that you want to reject null hypothesis. All right? So to construct critical value class, you need to know the degree of freedom. You need to know degree of freedom, which is n minus k minus 1. And you need to know the significant level that you want to reject null hypothesis. The standard rejecting or the rate, the significant level that you want to use is the standard one is 5%. All right. So for instance, you know that, all right, the degree of freedom is 522, and your significant level you choose 5%. What is critical value? The critical value with degree of freedom 522 and significant level 5% is 1.645. How do we know? Wait a minute. Let me share another screen in order to help you guys to find the critical value. minute. All right, so you go to your textbook and you need to find the critical value for T statistic, TMI. Can you see the share screen? Can anyone confirm?
Yes, teacher.
All right, so here, our degree of freedom is 522. But remember, for now, we only use one tail, right? So one tail, 0.05, all right, 5%. And then degree of freedom is 522. Here, if the degree of freedom is higher than 120, we choose this, all right? So here, if you can see, the degree of freedom 522 and significant level is 5% for one tail. Then the critical value is 1.645. So that's why we obtain this critical value. All right, that's why we obtain this 1.645. So here, then you can compare the T statistic and critical value. And you see now is T statistic is higher than critical value. So you reject null hypothesis. Hypothesis stating that there is a chance that population parameter equals 0. But here you say that no, we reject null hypothesis. We say that experience has significant effect on wage. In other words, you say that the effects, the true population's effect of experience on wage is not equal 0. So you reject null hypothesis. You reject null hypothesis. All right, I stop here. Question, everyone?
Sure. So if C 1% is less than 1.645, so we accept the null hypothesis.
If C is higher than T statistics, no, I do not talk about 1% yet. I only talk about 5%. All right. So now, if you assume that the significant level, the probability that you choose to reject null hypothesis is 5%, you will obtain the C value. All right. If C is lower than T, if C is lower than T, if T is higher than C, we reject null hypothesis. So in this case, T is 2.4, but C is only 1.6. So we reject null hypothesis at 5%. All right.
Yeah, sure.
What does that mean in simple, class? In simple, the meaning is that if you, all right, I try to find a simple word to explain. It might not be correctly reflect this, but I try to find a simple way to explain you. What do we mean by this 5%? We mean that if you analyze using the sample 100 times, all right, 100 times, 95 times, you will find that the coefficient is different from 0. What it means. Only 5% chance that the coefficient might equal 0. But 95% chance coefficient is not equal 0. So what that really means, right? I give you one example, a practical example, assuming, all right, someone, all right, someone developed COVID-19 medicine, all right, someone developed COVID-19 medicine, and then they want to test whether this COVID-19 medicine is effective or not. In order to do so, they need to conduct trial. They provide the COVID-19 vaccine to 100 patients. In order to make sure that the medicine is effective, they need to say that they need to choose the error. They need to choose the significant level. So they believe that it is called effective only if among 100 cases, 95% case is effective. If only 94% is effective and 6% is not effective, they don't call it is effective. All right? So that's what we really mean by 5% level. So again, this 5% significant level tells us that only less than 5% chance that coefficient might equal 0. But around 95% time, coefficient is not equal to 0 when the t value is bigger than critical value. Questions? Question, class? So far, this is the main point. To make an inference, make sure you know how to construct t-value and how to obtain critical value. But next week, I will tell you a next step. You don't have to care about this t-value or critical value. You don't have to remember this. Next week, we will discuss about p-value, and then you can look at p-value directly. It's much easier than this. But for foundation, you need to start with this. Questions?
Teacher, if it's bigger than 5%, it is significant or not
Yes.
significant?
So again, if t value, if t here is bigger than c, we reject null hypothesis. When we reject null hypothesis, remember what is hypothesis? Hypothesis stating that delta 0 equal 1. And our null hypothesis is that delta 0 is bigger than 0, right? So if we reject null hypothesis, we say that experience, the null hypothesis stating that the experience has no effect on wage is not true. So what we found here is that the wage significantly affect, experience significantly affect wage. Why? Because we found that we reject null hypothesis, we reject this one, but we accept this one. Why? Because we found that delta 0 now is of course bigger than 0. Sorry, delta J, not delta 0. Do I answer you?
So if it's significant, we reject the null hypothesis.
Right. When we say significant, again, class. When I say significant, I mean that when t is bigger than c, right? When t is bigger than c, we say that when t is bigger than c, the delta 0, the hypothesis stating that delta j equals 0 is wrong, right? It's not true. So if it is not true, meaning that there is no effect, right? If it is wrong, it is not true. The assumption that say that there is no effect is wrong. So what we found here is that there is an effect, right? Because delta j is of course bigger than 0. And when I say significant, is when we compare with 5%, right? So it is significantly, the experience significantly affects dependent variable, which is wage. Following me?
Yes.
All right. Sometimes we say significant, sometimes we say statistically significant, sometimes we only say only affect. It depends, all right? Class, can you follow me? All right. To reject or to accept null hypothesis, we need to construct T and C. How we construct T? It's the estimate minus population parameter divided by standard error. But in this case, we want to test the hypothesis that parameter equals 0. So when we replace it, it's only standard, the coefficient divided by standard error. And here, as you can see, t value is bigger than c. Now, when you look at this 5%, this t is when already bigger than 5%. When you have bigger than t bigger than c at 5%, you may want to explore more. Then you look at critical where the significant level at 1%. So if you look at critical value at 1%, so we go back to the table here. This is at 1%, right? So you scroll down and then you see that, oh, it is 2.326. Then you come back, you can see, all right, the critical value at 1% is 2.326. So T here is even bigger than C at 1%. All right. So you see the conclusion here is what? The conclusion here, the effect of experience on hourly wage is statistically greater than 0 at 5% and even at 1% significant level. This is the standard interpretation. Questions? So why do we need, when it is already significant, when it is significant at 5%, why do we need 1%? As I interpret in simple terms, if we found that 95% chance that experience affect wage is different from 0, then we may want to explore more. Is that really still correct if we use 99% chance? So here at 1% chance, we say that 99% chance we will obtain the coefficient of experience is different from 0. Only about less than 1% chance that this coefficient is equal 0. So you see, the lower significant level is the better, right? The lower significant level, the lower error, right? So if you test a medicine, do you want to have 95% effective or you want to have 99% effective? Of course, you want to have 99% effective. Right? Do you understand this? How to read this T table? First, you only start with one tail, all right? Then look at the significant level that you like and then degree of freedom. But again, as I said, the standard significant level is always 5%. 95% is already acceptable in social experiment, in social field. As long as it is 95% is true, it's good. It's good, right? 100 times, 95 times is already correct. Hopefully you understand how to read this table and how to construct this T value. Questions?
Sure. So we have two critical value, right, sir?
Again, you only need to choose one. 5% is good enough. But here, because this T value is very much higher than C at 5%, so the author, the researcher, want to explore more if it's still significant at 1%.
Oh, okay,
right?
sure. Understand, sir. I thought we need
Yes.
to choose two.
No, only one. 5% is enough. But from next week, when we come to regressions, we even have 10%. All right? We even have 10% in social science field.
So
Yep.
if our significant level is more than 5%, no, if the T is more than 5%, if we explore more, it makes our research more acceptable, right, sir?
It's more, you have more concrete result. All right. If your T here is higher than critical value at 5%, you can explore more if it's still significant at 1%. Why? You want to say that now we reject null hypothesis at 5%, and it's even better if you reject null hypothesis at 1%. I say again, a simple interpretation is that if you do it 100 times, if you choose 5%, 95% chance, all right, 95% chance that null hypothesis is not true. 95% chance that you find that experience effect on weight is not 0. But if you choose significant level at 1%, you say that 99% chance that the effect of experience on weight is not equal 0. The significant level in simple terms is the error, that you allow. All right, if you have 5% here, you believe that among 100 cases, only 5% that it's error. So if we interpret 95% chance that effect of experience on weight is different from 0, we may say that only 5% chance that experience effect on weight equals 0. It's just, an opposite interpretation. Got it? Adopt?
Yes, sir. Understand, sir. Thank you, sir.
Right? Class, let me be honest. If you don't understand the earlier part, make sure you understand this part. All right? This part is very important for application. I understand it may be a little bit complicated for you for earlier part, but this part, you guys need to understand this. Questions? Understand how to find critical value from the table. Understand how to construct the t value. All right. Again, class, we reject null hypothesis that delta t equals 0 only if t is bigger than c. But that is only true if we have null hypothesis stating that delta t is bigger than 0. Right? Only if delta t is higher than 0. If you have different null hypothesis, for instance, if you have if you have different alternative hypothesis, you believe that the effect is negative less than 0. This is another case. If you, for instance, you have, I don't have any idea whether this is positive or negative. You only say different from 0. Another case we will discuss after break. All right. So this is only correct, true only if your alternative hypothesis stating that the effect, the delta J is bigger than 0. All right. This is only the first case. And it's why we said that this is the testing against one side, alternative greater than 0, higher than 0. Question, please, everyone.
Teacher.
Yep.
Hypothesis is constructed from literature review, right?
Normally, it can be from literature review, it's from your own observations, right? Your own understanding of the context. For instance, what is the effect of COVID on dropout rate, right? Of course, you may read some literature saying there is a negative effect, but from your experience, you believe that COVID-19 will exacerbate the dropout, right? But again, in statistic class, null hypothesis always state that delta J equals 0, which means delta J has no effect on independent variable, has no effect on dependent variable. Did I answer your question, David?
Yes, teacher. Thank you.
So when you say that hypothesis is constructed based on relevant literature, it's only when you have no research interest. But when you have research interest, research class based on curiosity, right? If it's based on your curiosity, you may have your own assumption, and that own assumption can be called hypothesis. But in statistics, we always formulate alternative hypothesis with no effect. And then the alternative, it can be the effect is bigger than 0, lower than 0, or different from 0. Research is very simple. It starts with curiosity. But that curiosity, in order to prove, in order to answer that curiosity, you need scientific method. And here we use data, we analyze data from economic perspective. You can relate it to introduction to research class. Questions? I would love to have more questions, everyone.
Teacher, I have a question.
Go ahead, Mani.
I want you. I just want to have
it is like
we reject the null hypothesis is only when the T is bigger than C. So it leads to beta J is 0, right, teacher?
Yes. If T is bigger than C, meaning.
Can you hear me?
Not well, but I think I get your point again. we reject null hypothesis that stating that delta 0 equal 0. Sorry. We reject null hypothesis that stating that delta j equals 0 only if t is bigger than c. All right, only if t is bigger than c, and this is only when the case that alternative hypothesis is positive. All right, this is true only if your alternative hypothesis stating that the delta j is bigger than 0. That is the main point. So, for instance, you start with an null hypothesis stating that delta j equals 0, but you have alternative hypothesis stating that delta j must be bigger than 0. Then the way you reject or accept null hypothesis is based on this rule: t is bigger than c. If t is lower than c, we accept null hypothesis. We accept null hypothesis. Is that clear, Muni? That clear or what? Muni, you can ask a follow-up question if you are not clear. Guy, questions?
Teacher, if we accept, if a null hypothesis rejected, we accept alternative hypothesis, and if a null hypothesis is rejected, accepted, we reject the alternative hypothesis, right?
When we reject, right? When we reject null hypothesis.
So if we reject the hypothesis, meaning that the is affect on the dependent variable.
All right, let me say this again. If we reject null hypothesis, we accept alternative hypothesis. When we accept alternative hypothesis, we believe that independent variable of interest indeed affect dependent variable. All right, and if we believe it proves that your independent variable affect dependent variable. All right, but if you fail to reject null hypothesis, if you fail to reject null hypothesis or accept null hypothesis, you don't have to mention about alternative hypothesis. So you only say that, all right, when the t is lower than c, we fail to reject reject null hypothesis. So we believe that experience has no effect on weight at all. All right. Do we answer your question, everyone? I heard a question from a few of you, Davin and someone. All right. So
Actually, I
class,
have another question.
go ahead. Go ahead.
So what is the difference between like using the t and using the p value?
P is the next step. P is the next step. Normally, to construct P, you need T. And next week, you will discuss about P value. And that P value is the easier way to reject or accept null hypothesis. You don't have to compare with critical value. Your question is good, Varin, but we will discuss P next week. And again, in order to construct P, we need T value. So today, we are on the first step. Next week, we are on the second step. Is that clear, Varin?
Yeah, so basically p value is the final product that we use to like reject and accept it.
Right, correct. And again, we cannot compute P without knowing T. Today we need to know how to discuss T in order to compute P. Right. At the end, you can make final decision based on P. And make final decision based on P, your life is much easier. Your life is much easier. Because when we have P,
Understood.
okay, when you have P, you just look at P and then you will know it next week. I believe Vari understand P, but for now, you just always compare T and C. You always compare T and C. You may ask, why do we need it now? You know, step by step as a foundation. You need to understand it. Otherwise, when you study P and then someone say T, you don't know at all. Why? I give you an example of variant class. It depends. You know, in some report, they did not report p-value. If they do not report p-value, you do not know how to interpret. Some study, they only report T. All right. If they report T, at least you know how to interpret it from this class. All right. So instead that way, class, instead that way, researcher only report coefficient and standard error. If they only report coefficient and standard error, how do you know? Remember, this T is coefficient divided by standard error. And then you can remember the rule. Later, I will give you the rule of the critical value. All right, I will give you the rule of critical value. So that in the future, when the report only produce standard error and coefficient, then you immediately know, oh, T is the division of coefficient on standard error. Then compared to the general rule, you know whether this is significant or not significant. P-value is a good one only if researcher report that. But I said again, normally researcher only report coefficient and standard error. Why? Because if you remember from the beginning, we always discuss about unbiased coefficient. We always discuss about unbiased standard error. T is the product of standard error and coefficient. P is the product of T. So the most important point is if you get unbiased coefficient, unbiased standard error, you get correct T, you get correct P. So it's very, very important to understand coefficient and standard error. That is in most paper, they always report standard error and coefficient, not T, not P. All right. Any other question, everyone?
Got it, lecturer. Thank you.
Okay. Right. But don't worry. When it comes to data, I will teach you how to extract the table, how to extract coefficient and standard error, but also link with the p-value. All right. Let's have 30-minute break, class. It is now 6:52. Please return back to our room at 7. Now it is 53. Please return back to our room at 7:23. All right. Your 30-minute break start now. I see you after break. Hello, class.
Hello, teacher.
All right. Thank you, Chumin. All right, class. Let's continue our lessons. And after that, we will have a group presentations. Class. Before break, we discussed about testing hypothesis. Again, one-sided, which is greater than 0. In order to sub or reject null hypothesis, you need to make sure that t value is higher than critical value. How to construct t value? Standard error, coefficient minus hypothesized value. In this case, is 0 divided by standard error. How to obtain critical value? Select significant level. In standard way is 5%. Know your degree of freedom. And then look at the t distribution table, you obtain critical value. All right. Now let's move to another one. What if you have an hypothesis, an alternative hypothesis that is negative, right? The rule is the same, but the decision making now is depends on this. So earlier, when you have alternative hypothesis that you believe that the coefficient is bigger than 0, you reject null hypothesis if t is bigger than c. But for alternative that is less than 0, you reject null hypothesis if t is less than minus 6, right? So zooming again, we have null hypothesis stating that delta j equals 0. So delta j equals 0, but your alternative hypothesis now, you believe that there is negative. You believe that COVID-19 reduce household income, right? Null hypothesis state COVID has no effect on income. Alternative hypothesis state COVID reduce household income. So you want to test it, whether you will accept null hypothesis or you reject null hypothesis. If you reject null hypothesis, you accept alternative hypothesis. And again, 2, test again one-sided alternative that is less than 0. You reject null hypothesis if t is less than minus 6. And how to construct t? Standard error coefficient divided by standard error. How to obtain c? You need degree of freedom. You need significant value. All right. So now let's move next, for example. All right. We want to know whether class size has any effect on student passing math test or not. So in simple, we want to know whether school size affects math score or not. All right, math score as a proxy of academic performance. So the null hypothesis believes that the class size which is approximate by enroll has equal 0. It means that class size does not affect math score. Alternative, you believe that class size negatively affects math score. Class size negatively affects student performance. So here in this example, the number of observation is 408. All right. So now you have the coefficients of enroll, standard of enroll. You can construct t. You can find t. What is the degree of freedom in this case? Degree of freedom is n minus k minus 1. What is the k here? K here, 1, 2, 3. Right? Will you accept or reject null hypothesis. Hopefully everyone is here by now. So again, our null hypothesis is that class size has no effect on math test. Our alternative hypothesis, we believe that class size has negative effect on math test. Is that correct? All right. Next, let's generate T. T here is the coefficient minus 0.0. Standard error is 0.2. Is that correct? Right? And now we obtain T score is about minus 0.81. What is degree of freedom? Degree of freedom n minus k minus 1, 408 minus 3 minus 1. We obtain degree of freedom at 404. So with degree of freedom 404 and significant level at 5%, we obtain around 1.65. You have to look at the T distribution table. And based on the rule, the negative C is minus 1.65. Dear class, we'll do a sub or reject null hypothesis. We accept null hypothesis only if T is lower than minus C. What is T? T is this. What is minus C? Minus C is this. Do we accept or reject null hypothesis?
Accept, sir.
Right. So we fail to reject null hypothesis. We can say we accept null hypothesis or we fail to reject null hypothesis. All right. So at the critical value for 5%, the minus C is bigger than T. Right. The minus C is sorry, I think I'm wrong.
Sure.
Right.
Sure. If C is equal minus 165, so minus C is equal 165, right, sir?
No. This one is already minus C. This one is already minus C.
Oh, okay, sure.
C normally is value, but here it's just a negative C. All right. So in fact, it is the same value as T earlier, that is 1.645. But when we round up, it becomes 1.65. And negative C, it becomes minus 1.65, the same value as the about the earlier critical value for 5%. Right? So here we obtain T lower than C. Right? So in this case, we fail to reject null hypothesis, or we say we accept null hypothesis. So in this case, class size has no effect on math score. Right? So here you look at the bold statement underlined here. One, you cannot reject the null hypothesis that there is no effect of school size on student performance. All right? You cannot reject null hypothesis. And that hypothesis is that there is no effect school size on student performance. Not even for significant level at either here 5% or even 15%. But here, if 15% is not significant, you see, we even increase the significant value to find it more. But even at 15%, still T is lower than C. All right? T is lower than C. Question, everyone? Did you follow me? It's the same, right? It's the same. Practically, they are the same.
Hello, teacher.
Yep. Now,
Can you clarify about the t value, t critical, t statistic? What are the difference?
When we say t value or t statistic, it is the same. But critical value, it is different. Critical value is you obtain when you know degree of freedom and you know the significant level that you choose. And to obtain critical value, you need t distribution table. All right. You remember I showed you earlier how to read t distribution table, and to read that you obtain critical value. All right. Again, t value and t statistic, when I say it, it is the same. Then we need to compute it by coefficient divided by standard error. For the critical value, you need to know this degree of freedom and significant level that you choose, and then look at the table to determine it. Is that clear, Samang?
So there is one more t, which is t table, right?
That is, we call t distribution table. That is not about t, but we call that t distribution table. You need to look at it to find critical value. Remember, before break, I show you how to read the table. Let me quickly show you again. All right. All right. Hopefully you see the screen. Now you have to go back to the table. We call t distribution table, but we want to find critical value, not t statistic. All right. We want to find critical value. Come here and then you find this table. All right. Here. We use one tail. All right. If you look at our example, we use one tail. One tail. Degree of freedom 404, 5%. Here, 5%, one tail. Degree of freedom 404. It is close to infinity. So it is 1.649. Round up, you get 1.65. And minus C is minus 1.65. Got it, Samang? This is how you obtain critical value.
Yes, sir. Thank you.
Right,
then let me get back to our...
Sure, one more question, sir. What does
Yep,
K stand for, sir?
K?
Yeah, K in degree of freedom, sir.
Again, K, the number of independent variable.
Oh, so it has 3, right, sir? And we have...
Yes.
Okay.
Right here. This is number of observation. This is 3, this is 1. And this, we call it degree of freedom. We call it degree of freedom. This n minus K minus 1 here. All right. So let me get back to our original screens.
Because when I check Google, they say degree of freedom only equal to n minus 1, sir.
N minus 1 is only when with linear regression.
Okay, sure.
But with simple linear regression, you only have one explanatory variable. That
Yes,
is, right? All right, you got it. All right. All right, class. This is when you have different alternative hypothesis. All right. Now, let's have a look at another example. What if we change functional form? All right. Earlier we used here. If you look at this example, hopefully you see the screen. We use non-natural logarithm. We use its original form, but now we transform the variable to natural logarithm. All right, we transform our variable to natural logarithm. When we transform our variable to logarithm, you see the null hypothesis is no longer b of in row, but b of log in row. And our null hypothesis now is b of log in row. Here you already obtain coefficient, you obtain standard error, and this time when you compute t, you find a larger t. And this time t is This time t is lower than -6. So this time you reject null hypothesis. Earlier, when you don't transform the variable, you accept null hypothesis, saying that class size has no effect on math test at all. But when you transform the independent variable to natural logarithm, you see that now t is smaller than -6. So now you accept reject null hypothesis. What do we get from here? What we get here is that, you know, functional form is important. So when you read the literature review, you have to know why the literature review use log or non-log. Then you have to follow that because they have some assumption in their mind, or because of data, right? Again, when they don't use log, as you can see here, as you can see earlier, t value is small than critical value. Bigger than critical value. But when we change to log, we get t value is lower than -6. This time, the hypothesis that there is no effect on student performance can be rejected in favor of hypothesis that effect is negative. See, only difference functional form. One is non-log, another one is log. We produce different result. We have different result. It's very important for functional form. And remember, one of the motivation of using multiple linear regression, it allows you to use flexible functional form. Following me, class, with this example. Simply just change the functional form from non-log to log. We get another result. It's very interesting. Very interesting.
Sure. So this means if we use functional form, it is more clearer, right, sir?
It depends. It depends. For example, in this example, whether you should use log or non-log, it depends on your reading. It depends on data, right? If data is not normally distributed, you want to use log so that it is normally distributed. Or when you do some reading, the author tells you why they use log. Because I am not in this field, I don't know why. But I believe that one of the reasons is that they believe that the data or enrollment rate is not normally distributed. It doesn't mean that you always need to use log, everyone. It depends on the problem. One of the problems that we use log is because we want to have normal distributions. And also, how do we know that? Literature review. When you read the existing study, they tell you what model they did, why they use natural log, why then they use, right? Got it, Adam?
Yes, sir.
Right, class. With functional form, the only way you know is to do reading. All right. Identify relevant variable, functional form. Reading tell you. Microeconomic theory tell you. All right. Before we come to econometric model, you need econometric theory. Economic theory. What is that theory? It tells you what is the. For instance, if I want to assess the effect of price on quantity demanded, I know what I should include it in the model. I should know that from economic model, economic theory is that if I want to assess the impact of price on quantity demanded, I have to include substitute good, complement good, right? So based on economic theory, based on existing study. All right. So next, now we discuss about testing again two-sided alternative. What is two-sided alternative? Remember, earlier on, null hypothesis always start that delta J equal 0. So when you know, for instance, you believe that COVID has positive effect on dropout rate. When we say positive, it means that it's on the same direction, right? When we have positive, when there is COVID, dropout rate get higher. So we believe that COVID has positive effect on dropout. If that is the case, you use one-sided greater than 0. However, another study, when you want to estimate the effect of COVID on income, you believe that alternative hypothesis is negatively affect on income. But at one point, you said, I don't know the direction. I don't know whether this is positive or negative. So you can say my null hypothesis is different from 0. When it is different from 0, it means that it can be positive or it can be negative. All right. So you are not clear about the direction, but you believe that the effect is not 0. There is some effect, but I don't know whether this is negative or positive. So if that is the case, you use testing again, two-sided alternative. All right. You use testing alternative, testing again, two-sided alternative. And how to obtain t value and c and critical value? The same rule. But this time, to reject null hypothesis, the rule is absolute t. When we say absolute t here, t can be negative. If it is negative and we put absolute, it becomes positive. So absolute t must be bigger than c, must be higher than c if you want to reject null hypothesis. All right? Absolute t, not simply t. If it is minus, when you put absolute, it becomes positive, right? The absolute t must be higher than c. Because we do not know the direction, our alternative here, it can be positive or it can be negative. If it is negative, we need to use the absolute t to become positive and make sure that the t value is bigger than c. All right, the same rule. Now let's have a look at the example. Class, we want to estimate the effect of attendance, the absent number of absent on collect GPA. We want to know whether those who are absent have negative effect or positive effect on GPA. But assuming that we do not know whether the direction is positive or negative. So in this case, our alternative is different from 0, not negative. And in practical way, class, you can, if you don't know direction, always use two-sided. If you use two-sided, make your life easier. You don't have to worry about the decisions root. All right. You just remember that absolute t is higher than c. Two-sided make your life easier. And in Stata or any applications, they always produce t value from two-sided. Right? They always produce value from two-sided. So from now on, it's best for you guys to use two-sided. Make your life easier. All right, here. I want to assess the effect of skip. All right, the absent on collect GPA. Now I obtained the coefficient and standard error. I know number of observations. All right. So how to generate t? How to generate t? You already know it. T is the standard error divided by, the coefficient divided by standard error. Right? Divided by standard error, you will obtain t. And this is t. All right. This is t for high school GPA. No, this is t for this one. And we want to look at t skip, and this is t skip. All right. T skip is minus here. We obtain minus 3.90. And about critical value now it's a little bit different, class. It's a little bit different. Let me show you back the original screen. All right. It's a little bit different now because you use two-sided. All right. When you use two-sided, when you look at the table, you also need to choose two tab. Can you see my CR screen, everyone? Can anyone confirm? I am now on the critical value. All right. So here for two-sided, you have to look at the row two tail, and then 5% or 1%. For example, in our example here is at 1%. All right. So if at 1%, and then degree of freedom, how many? The degree of freedom is 141 minus 3 minus 1. So we have 137. So 137 and 1%. Here we just follow example. If we obtain the same score, right? So two-sided 1% is here, all right? This row, and then 137, it is close to infinity, so we obtain 2.576, right? 2.576. And back here, and that round up to 2.58. You see? So for skip, coefficient is negative divided by standard error, then you obtain negative t-value. And when you put absolute, it is equal 3.19. And this 3.19 is bigger than critical value 2.59. So in this case, do you accept or reject null hypothesis? All right? For skip. So in this case, we reject null hypothesis. We say that the skip has significant effect on college GPA. This is when you want to look at skip. You can test high school GPA. You also can test the average test score, ACT, here, from the previous example. Let me get back to our screens. Can you follow me, class? So the reading the critical value in distribution table is slightly different if you decided to use one tail or two tail. Questions? Can you follow me? Any clarification or doubt you guys want to make? All right. Thank you, Davin, for your chat. Let's wait a few minutes in case someone want to ask questions. So the key message, the takeaway for today is how to compute T, how to read critical value, compare T with critical value, whether you accept null hypothesis or reject null hypothesis. Null hypothesis always start with no effect equals 0. Alternative hypothesis can be negative or positive or different, but it's best, it's good. If you don't know the direction, just say it is different from 0. Right? Just say this from 0. Using two-sided, the life might easier. Why? Next, there is a general rule. All right? There is a general rule that you don't have to come to have a look at the critical value at the table every time. Question, please. All right. No questions? Can I have a look here? Do we accept or reject null hypothesis for T high school GPA? Accept or reject? How about T average class? Sorry. How about T ACT? Do we accept or reject? You don't have to answer me. Ask yourself. Do we accept or reject null hypothesis for T high school GPA? Do we accept or reject null hypothesis for T ACT? For skip, I already informed you. I already told you that we reject null hypothesis.
We accept ACT.
ACT we accept, right? Correct. Down. Right. So and T GPA is the same, right? So here, as you can see, this is the interpretation. The effect of high school GPA and skip are significantly different from 0 at even 1%, right? The effect of ACT is not significant different from 0, not even at 10%. When there is no significant, you always start to increase the significant value. When it is significant, you always start to reduce the significant value. You want the lowest one, right? All right. That is about the hypothesis testing using T, and this is the general rule. All right. So what again? When we say statistically significant, it means that the T is higher than critical value for two-sided. All right. So if a regression coefficient is different from 0 in a two-sided test, the corresponding variable is set statistically significant. So what do I mean by statistically significant so far is this. When the coefficient is different from 0 in a two-sided test. What do we mean by coefficient different from 0? T, absolute T is bigger than 6. That means we say statistically significant. So if it's 5%, 90% correct, only 5% error. If 1%, 99% correct, only 1% error. Right? If the degree of freedom is large enough so that no more approximately apply, the following rule of sum can be applied. Meaning that if you have large observations, so when you have large observations, you have large number of degree of freedom. If the degree of freedom is large enough, when we say large enough, I believe it's more than 120, the degree of freedom. So as long as you have large sample, then it make you have it allows you to have large degree of freedom. If that is the case, remember this: critical value at 10% is always 1.645. Critical value at 5% is at this. Critical value at 1% at this. If you have T value, you can compare with this. Or in short, if your T value, if the T value of T statistic is bigger than 1.645, you always reject null hypothesis. So you don't have to always look at the table. Remember this 3 critical value, that is enough. If you want to test your hypothesis using T, but next week you don't have to remember this value. We only use P value, what we asked earlier. Question, everyone? Any? Question,
No.
any?
No.
All right. No. So this is the general rule. If you remember this general rule using two-sided, that's it. You don't have to look at critical value. You don't have to look at the table. That is all for the first part of inference. Next week we'll discuss more how to construct P, how to construct confidence interval. So that I will explain for you more to make more sense. What do we mean by a chance? Why we say it is equal 0? I will explain you more next week. All right. That is all for today for the first part. All right. So let me recap again. The importance for you guys today is to know how to compute T and how to obtain C, so that you can know when you guys are going to accept or reject null hypothesis. This is for the purpose of hypothesis testing. All right. But again, it is also good if you remember the assumptions. All right, the assumptions. All right. To relax your brain, yeah, go ahead, Adam.
Sure. Only one question. Sure. So if T ratio more than 1.645, statistically significant at 10% level, so it means there are 10% chance we accept the null hypothesis, right, sir?
No, this is the significant level we talked earlier. When we say 10% here, 10% level here, we allow error only 10%. We allow error for 10%. For instance, if your null hypothesis stating that education has no effect. Education has no effect on wage, right? Then only 10% is error. You get what I mean?
Yes, sir.
All right. So here's the chart. Right. That is the main point. So what I'm saying here is that, for instance, if you are looking at investigate the effect of education on weight and you decided to use 10%, so it means that among 100%, if you reject null hypothesis, you use 10%, 90%, 90 times among 100 times, you will find that education has significant on weight. Only 10% chance that education has no effect on weight, right? So here, this significant level is a type of the probability of getting the incorrect answer, right? You get what I mean? So when we say significant here, for instance, if education significantly affect weight, we say that 90%, if you conduct the survey 100 times, if you analyze 100 data, 90 times you will find that education significantly affect weight. Only 10% chance that you may get it not significantly affect weight. Is that clear now?
Yes, sir.
All right. So again, this 10% significant level here, it might not correctly interpret the original meaning, but you can say it like this. You can say that this is a chance of error, right? The chance of it is not significant. The chance of it is the chance of error. All right. All right. So let me close today. Let me finish our lecture here, and let's change, relax your brain a little bit. So last week we have group presentation from group 1 and group 3, and as you remember, group 3 did a good choice on selecting a paper that is appropriate at your level, right? That is good for your level. And today we gonna have 1 or 2 more presentations if time allows. We have around 30 more minutes to go. Any group would like to volunteer?
Group 6, sir.
All right. All right. So we start with group 6. Floor is yours.
Okay, Bro Quang, please share.
Hello, teacher. Can you hear me?
Can.
Yes.
Có bạn bật share screen. Okay, let's start. Good evening, teacher, and good evening, classmates. And today our group will presentation about the topic is the trade-off between the inflation and unemployment in the short run in the case of Indian economy. This is our team member, Hai Phụ Đắm, Sum Nang, Quang, Me, Sun Hua, Satikun, and last one is Sinasa. Let's move on to the next slide. Quang, move to the next slide.
Miên khơi nhau miên mô
Not yet. Yes, I see. Now back to content. Now let's move on to content. Let's begin with the introduction, followed by the theoretical framework and the literature review. Next is the methodology and data source, followed by the data analysis and discussion of result, interpretation of result, and the last but not least is the conclusion. Let's move on to the next slide. Yes, let's begin with the part is about the introduction. Like we all have known that there are many discussions on the relationship between the inflation rate and the unemployment rate, because both of them are the key indicator of an economy. And moreover, the dispute between the inflation rate and unemployment rate still continue, it still exists until nowadays, because for the scientists, they agree only with the long-term period. So we have set the point of the target to find the actual connection and find the influence on each other. And also if there are any trade-off on these two indicators. To answer all of this point, we have solved it through the Philip curve, the curve that we call Philip curve, to see the evaluation of the economy for inflation and the unemployment rate in the last century. This is the end of my point, and I want to give the floor to the next presenter to present about the theoretical framework and literature review.
So the current part is about the theoretical framework and literature review. So the theoretical framework, as it has seen in the slide, the Philip curve was named after the British economist Philip who first examined the relationship between the rate of unemployment and the money wage. And there was an analysis of his that based the data in the UK between 1861 until 1957, and it showed the result of the empirical that there was the inverse relationship between the rate of unemployment and the rate of increase in money wage. And for instance, when the unemployment was high, the wage increased slowly, but the unemployment was low, wage rose rapidly. So next slide. Yes, so the next one is inflation literature review. So there was the argument in 2010, Garanasu and Salas, at there was the trade-off between inflation and employment in the long term due to the growth of the money and productivity, that these both could lead to the decrease in employment, and well as the supply shock like oil price can lead to an increase in employment. For instance, in the case of 1970, the expansion of monetaries that it leads to increased inflation and reduce the employment. So Daniel Berger has shown that the conventional model of Philip curve failed to capture the effect of employment on inflation, and there was an increase in clinical employment that could generate a fall in output, which lead to a decrease in inflation. That's all for my point. Move on to the next presenter. Thank you.
So move on to the third part. We're talking about the methodologies and data source. So in this research paper, the ordinary least square methods and bivariate regression model of the econometric approach was used in the estimations, and for the bivariate regression model is it is a study for the associations that they use for testing to see whether there is a relationship between two variables with statistical analysis, and also to study the empirical on the relationship between unemployment and inflation in India economy. There are three models that will be employed. The first model is about the inflations and real GDP that will be regressed on the unemployment. And the second model is about unemployment and real GDP will be regressed on inflation. And the third model is about the inflations and unemployment will be regressed on real GDP. So, like, to explain this model, like for example, the first model that they said that the inflation will be the inflation real GDP will regress on unemployment. It means that they testing about the inflations and real GDP, whether this relationship, whether they have relationship with each others and it affect to the unemployment or not. So it's same goes to the second and the third one. And as you can see on the right side of each model, there are a written function form, which the UNEMP is stand for unemployment rate, INF stand for the inflation rate, and GDP is refer to real GDP. And about the data source, they are the secondary database which period from 2009 and 2015, and the source are from the Central Bank of India Statistical Bulletin, which the data they take they get on real gross GDP productions and data on consumer price index for the inflation, and also the data on the Ministry of Labor and Employment for unemployment rates. And so that's it for the third part, and move on to the next one.
So we are looking at data analysis and discussion of results. So in table 8, you can see the descriptive statistic of unemployment, inflation, and real GDP. So looking at the unemployment rate, you can see the maximum value and the minimum value, it has a little gap. So that means that unemployment is very consistent and less volatile. While on the other hand, inflation, the gap between the maximum and minimum value are wide, which means it is very inconsistent and volatile. Move on to the next slide, please. So this is there are three models for regression between unemployment and inflation, unemployment, real GDP, unemployment, and inflation. So for the first model, at the top left side, the R square of 0.76, it shows that 76 variation in unemployment is explained by inflation and real GDP in the first model. And they adjusted R square, the value of 60, which show that 60% variation in dependent variable is explained by independent variable when the degree of freedom is taken care of. The F-test value for unemployment and inflation is greater than 0.1975, which indicate that the rejection of hypothesis that there is a causation between inflation and unemployment. This confirms that unemployment substantially affects inflation, while GDP has little substantial effect. And for the second model, the R square of 0.96 illustrates that 96 variation in inflation rate is explained by unemployment and real GDP. The adjusted R square of 93% show that of 0.93, so that 93% variation in dependent variable is explained by independent variable when the degree of freedom is taken care of. And the F-test is higher than 0.007. So this rejects the hypothesis that there is no relationship between inflation and unemployment. And this confirms that inflation substantially affects unemployment, while real GDP has substantial effect. And for the third model, the R square is 95%. And the adjusted R square show that 91% variation independent variable is explained by independent variable when a degree of freedom is taken care of. And the F test is 29.36, and it is more than the significant level of 0.01. So it indicates the rejection of hypothesis that there is causation between unemployment and real GDP growth. And this confirms that real GDP substantially affects unemployment, while inflation has little substantial effect. Move on to the next slide.
Yes, hello. Let's move to the interpretation of result as the tables. As the table 10, we can see that when all variable hold constant, the intercept of real GDP is at around 8.55%. I think this refers to the third model, the below part. And based on coefficient of unemployment, real GDP will decrease by 1.72% if unemployment increased by 1 unit. And based on the coefficient of inflation, unemployment will decrease by 1.6, around 1.67%. 1.67 if explanatory variable inflation increased by 1 unit. And about the elsewhere, I think Dom has also explained it earlier, so I want to skip this part and move to the t-test. And the t-test is used to test whether independent variable is significant to dependent variable or not. And under n minus k degrees of freedom and at a 5% level of significance, the critical value is negative, positive 4.92%. 4.92, and so we reject the null hypothesis that the variable is statistically insignificant if the t critical is bigger than the t table in absolute values, that is ignoring the negative values and accept in both the equation. And here is the tables of the three model: unemployment, inflation, and real GDP. And for the hypothesis testing, the first hypothesis is that there is no short-run trade-off between inflation and unemployment. Second hypothesis is there is a significant relationship between inflation and unemployment. And the last null hypothesis is real GDP has no significant impact on unemployment. And the F test. For the F test, the decision rule as stated previously is to reject null hypothesis that the model is well specified and adequate for forecasting and policy analysis if F critical is bigger than F 0.05 and accept it if otherwise. Just move to the conclusion. As the findings show that the unemployment coefficient is positive and statistically significant while inflation is negative. And yes, this paper suggests that some policy options such as restructuring the economy through inward growth, efficient modern technology, ensure macroeconomic management of price instability, and improving infrastructure. Yes, thank you, and that is all from our group.
All right, thank you. Let's see if we have time for the group 2 presentations. First of all, class, any comments on the group 6 presentations? All right, class, let me give some comment, but not presentation, but on the paper. First of all, this paper is not a good paper. The way it's summarized does not make sense, and it is not correct. Right, it's not correct at all. First of all, let me ask the group 6 equation. Group 6, do you know what is the data that employed in this paper? Cross-sectional, time series, or panel data?
I think it's time series because it show yearly between 2010 to 2014.
For Indian, right? Good.
Yes,
correct. Correct. Done. Right. Next, so far we only discussed multiple regression, and as I said, we only use cross-sectional data. So it is a little bit difficult for you guys to understand this paper because this paper employs time series data. Even though the author did not mention it is time series data, but as you can see, the same poly is only for India from or time period. If that is the case, linear regressions or multiple linear regression is not a good model for running time series data. First comment. Second comment. If you look at the research question and topic, they say trade-off, whether this is a trade-off between inflation or unemployment. Did you guys find the answer? Is there any trade-off or not trade-off? Good topic or good research question or paper always answer the question. What the conclusion? For Dom?
Don't know, Chair. The Indian answer doesn't say anything, Chair.
Right, you look at the topic. The topic is about trade-off between unemployment and inflation. But if you look at the data, I am so confused. I don't know. I don't know what is that. You know why? If you look at the regressions, they run different regression. Regression when they use first inflation as dependent and then unemployment as independent, and then they run GDP as an independent. That is the case that is true. But again, that is confusing for now for you guys to understand. But I just want to point out that the author should answer to the question or to objective. For now, it's not easy for you guys to understand. But in terms of organizations, if you want to learn from this paper, it is not good. It is not good for your level, but probably next you will understand it. And here, the author, for instance, when it comes to slide number 8, the author explained about F-test, about the model. You did not study yet. We will talk about it next week or the following week with F-test. The F-test, you need to know what is the hypothesis when using F-test. F-test is something that you do not answer yet. So I would say this interpretation based on the slide number 8 is not really correct. Because F-test is explain the model as a whole, but when you write down the statement based on this test on slide number 8, it is not reflected with the table. It is not correct. All right. So I would, in short, I would say it's difficult for you guys to follow this paper. This paper is not a good model for you guys to follow. All right. If you guys plan to do your group assignment based on this paper, I would suggest you guys to change the paper. It is not a good one. And also it is using time series data. I don't know if you can do it with, you don't have enough data to analyze it as well. And don't follow it. This is not a good practice. This is not a good practice. All right. Again, we will learn it when we come to time series data. We will touch on it with time series data. Normally, OLS is not a good model for running time series data. When we come to time series data, we have to talk about whether data is stationary, whether there is a unit root or not unit root. All right, we have to discuss that with time series data. Let me stop here. I would suggest you guys to find another paper, but at least you should learn if you are going to look at the inflation or unemployment, it's better to specify what is your independent variable of interest and what is your dependent variable of interest. But here you cannot find it. All right, guys? Group 6, you have to know what is your X, what is your Y, and what is other independent variable should you include in your model. All right? That is the key takeaway from your group. Okay? Any question, group 6 or everyone? All right, Singha, group 2. My apology, we will not be able to have another presentation because we have only around 5 minutes left. Let move your group to next week. Is that okay, Singha? Group 2?
Yes, that's okay, lecturer.
Right. Any question, everyone? So group 6, it's better for you guys to find another paper, not this one.
Hello, teacher.
Yes, go ahead, Shimei.
When do we have midterm?
No midterm. Look at the guy. Guy review the syllabus. All right. If you have any question, any doubt, first of all, look at the syllabus, and then if there is no information in syllabus, then you can contact me. There is no midterm for this course. Only final. We only have, if I remember, we have lecture note, you have quiz, you have group assignments, you have presentation, and you have final. Okay? If you worry about final, try to familiar with quiz.
Teacher,
any questions?
When is the deadline for term paper?
All right. I want to tell you guys that the deadline for term paper is a week before final. A week before final. So you should start as soon as possible looking for data. Next week I will share with you some potential data. But again, that potential data need your time to do more reading on the textbook. For instance, you guys need to read a textbook on using data for principle of economics, so that you can understand some data, so that you can follow some example from the textbook of using data for principle of economics. I will share some potential data next week. But if some of you have data and you want to proceed, go ahead. Don't wait for me. What I want to share is just only if you don't have data, you have no choice. You may select some data from the data set that I will share next week. All right? So start soon as possible. Questions? All right. So class, today we discuss about hypothesis testing. You learn how to accept or reject null hypothesis by computing t-statistic, comparing with critical values. All right. Next week, we will discuss more on how to compute p-value. Not how to compute, but more how to interpret, because it is another way. And we also will discuss confidence interval. If there is no questions, allow me to close our section today. We finished 2 or 3 minutes early. That's a good point. All right. I'll see you next week. Stay safe and take care, everyone.
Goodbye, teacher.
Bye-bye.
Goodbye, teacher.
Bye, yeah. Guys, thank you. See you next week.